This is the second part of our three-part lecture on basics of linear regression in R. In the last segment, we learned about some very basic steps to run a linear regression in R, and we took a look at some commands from the Broom package, including tidy, augment, and so forth. Now we're going to talk about a special issue that comes up when we're trying to specify a linear regression model, and that is dummy variables. So dummy variables are variables that are either 0 or 1. They're sometimes called binary variables, and you could manually create dummy variables using dplyr and use them to encode categorical information. So if you wanted to encode, let's say, 3 or 4 different categories, you could have one dummy variable to be 1 if category 1, another to be 1 if category 2, another to be 1 if category 3, and then an omitted category. You could do this, but it's a waste of time and it's a huge waste of memory on your computer. It may also be quite unclear. So I can remember many times when I've opened up someone's Stata data set and they have a variable called sex. And when sex is 1, without seeing the codebook, I have no idea what that means. It could mean either male or female. So my advice to you is to store categorical variables, not huge collections of dummy variables. Store a genuine categorical variable that has meaningful names that tell you what the data means. Then R can create the dummy variables for you behind the scenes before it runs the regression. Let me show you how that works. But before I do, let me just remind you about the dummy variable trap. So a categorical variable is a variable that has no meaningful order. For example, eye color. Now, we cannot include an intercept and a coefficient for each level that a categorical variable takes on. For example, we can't have an intercept, a male dummy, and a female dummy. Why not? Well, that one dummy for male would be linearly dependent with the female dummy given the presence of the intercept, because the intercept is just a column of ones. So you could perfectly predict the male regressor using the column of ones and the female regressor. And that would mean that x prime x can't be inverted, so there is no unique solution for the OLS estimator. Of course, this is easy to fix. All we've got to do is drop something. So we could either drop the intercept or we could drop one category. That's a category that we typically call the omitted category. So let's try this out in R. The first thing I'm going to do is I'm going to follow my own advice, and I'm going to change the kid's data set so that this mom HS variable takes on more meaningful levels. So I'm going to use a mutate command along with the if-else command to say that if mom HS equals 1, I want to record that as the character string HS, which stands for high school. Otherwise, no HS. And you could use even more indicative names than I have here. Those were just the ones that I came up with. Okay, so now what happens? What happens if I try to run my regression? Well, I've just changed mom education from being a numeric vector to being a character vector. So how can I regress kid score, which is numeric, on character vector? Well, when R sees this, it realizes what I meant. What I meant is that I want to have this mom education variable treated like some collection of dummy variables. And indeed, I only need one in this case because there's only 2 categories. So what we see here is the result of running LM. We have an intercept, as we've always had, and then we have this funny-looking coefficient over here, mom education no HS. So what does that tell us? Well, that tells us the coefficient on a dummy variable that takes the value 1 if mom education is equal to no HS. R has helpfully given us a lengthy descriptive name that makes that clear. Okay, so R has told us exactly how it encoded the dummy variable. But unhelpfully, it has actually chosen high school as the omitted category. Whereas I think most of us, if we were asked which of these categories we wanted to drop, we'd probably drop no high school because we want to think about some kind of change that occurs as someone gets more education or some kind of difference between low to high. So we may have a preference for omitting one category versus the other, and R has kind of unhelpfully chose for us. So the next thing I'd like to show you, it's very convenient that R constructed the dummy variable, mind you, but the next thing I'd like to show you is how we could specify which category we'd like to be dropped. We can do this using the FCT relevel command, which you may recall from when I introduced dot plots in our ggplot lecture. This is a command from the for cats package, which is part of the tidyverse. So if you have installed tidyverse and you have loaded tidyverse with the command library tidyverse, then you've already got access to this package. I'm not going to go into a tremendous amount of detail about this command. If you want, you can read about it by following the links at the bottom of the slide. But I will just show you that you can use it to specify which category you would like to be the omitted category by using this FCT relevel command for mom education, and then specifying that no high school is the omitted category. And now what we see has happened is that the label on that regression slope coefficient says mom education HS, which is our way of telling us that this is the coefficient on a dummy variable that equals 1 if mom education takes on the value HS. Notice that this coefficient, 11.77, is exactly the negative of the one that we had before. And that makes sense because all that we've done is change the omitted category. There is another option, which we will discuss below. Instead of omitting one of the categories, it's also possible to choose to drop the intercept. And I will comment on that when we get into some of the nitty-gritty of our formulas in a couple of minutes. Not a couple of minutes, a couple of seconds. I really should look ahead on the slides. Fun with our formulas. There are so many weird and exotic things that you can do inside of our formulas. I'm only going to show you the basics in this lecture. If you want some more details, you can click the link on the slide and you'll be taken to my blog, Read Often, Subscribe Often, for an R formula cheat sheet that explains some of the more exotic ones. So we've already seen y tilde x. That's in our formula. It's used to specify a statistical model, not just in linear regression, but as we'll see later on, logistic regression and lots of other places. But within a formula, certain characters have a special meaning. We've already seen tilde and plus. Plus does not mean addition inside of a formula. It means I'm going to separate one right-hand side predictor from another. And plus is just a way of indicating, hey, the thing to the left and the right of this are different variables. The other symbols that have special meanings, the other characters that have special meanings in formulas are dot, minus, 1, colon, asterisk, caret, and then this guy, capital I parentheses. The caret and multiply are a little bit more exotic. I'll skip them here. But again, if you want to find out more about them, you can consult my R formula cheat sheet. First of all, the dot. The dot means everything else. So the formula kid score tilde dot means, hey R, I would like to regress kid score on everything else that is contained in the tibble that I've given you. So here we're going to regress kid score on everything in the kids data frame except for kid score itself, of course. So as you can see, we now have coefficients for every single one of these variables. Notice that the coefficient on mom education HS is NA because this one has been dropped. This is the dummy variable trap. When I created the mom education variable, that was a kind of a recoding of the mom HS variable. And so now it's redundant. Minus is used to remove predictors. The most common reason that you'd want to use this is if you're combining it with dot. So let's clean up the issue that we saw on the previous slide, which is I had two variables I was trying to include in the regression that actually represent the same information. So let me get rid of that redundant mom HS predictor. I can do that by writing the formula kid score tilde dot minus mom HS. That tells R that I would like to run a regression of kid score on everything inside of the kids data set except for mom HS. And as you can see, we're getting exactly the same coefficient on mom education HS as we got on the previous slide for mom HS because they encode exactly the same information in exactly the same way. The next thing that we need to know about formulas is 1. 1 is a way of referring to the intercept. Now, by default, R is always going to include an intercept in a linear regression. But if you want to remove it, you can. So here is how you do it. I'm going to have kid score tilde dot minus 1. So what has happened here? Well, there's no more intercept, but now R has managed to include both mom HS and the dummy variable mom education no HS. So what's happening here? Well, R has now managed to include both the dummy variable for when the mom attended high school and a dummy variable for when the mom did not. These would be linearly dependent if there were a constant in the model, but there isn't, so it all works fine. We could also use this one, which again takes on a special meaning in a formula, to run a regression on only an intercept. It's a bit of a silly thing to do, but that just calculates the mean of the kid score. Okay, so why do we want to remove the intercept, and when might we want to do it? Well, it's usually a bad idea to run a regression with an intercept because that forces us to make a prediction that y is 0 whenever x is 0. But with dummy variables, as we saw on the previous slide, excluding the intercept can give us an alternative parameterization of the model. So if you go back to the previous parameterization where we omitted one of the categories and we included an intercept, then the coefficient on the mom education high school told us the difference of means in kid scores for the mother who went to high school versus the mothers who did not. In this new parameterization, where I remove the intercept, we are instead estimating and displaying a separate mean for each category. It's exactly the same information in the sense of the predictions that it makes, and we will draw exactly the same inferences if we care to do so, but it's just a different way of representing the information. And again, if you find any of this regression interpretation stuff difficult to understand, at the very beginning of this set of slides, you can click on a link that will take you to a document from my undergrad course where I walk through exactly the same regression example as you see here, but I go through all the details of exactly what these different formulas mean. So if you do find this puzzling, I suggest you go back and take a look at that before watching the rest of this video. Sometimes we may want to transform outcomes or predictors. There are a number of different ways that we could do this. One way is using dplyr. Here I've got a pipeline in which I use a mutate command to convert kid score to the log scale. Honestly, that's a silly thing to do for a test score, but I'm going to do it anyway. So I'm going to compute log kid score is equal to the natural logarithm of kid score. And then I'm going to compute mom age squared. Mom age squa is equal to mom age raised to the power 2. Once I've done that, I have a new tibble, which I'm calling new kids, which includes some extra columns, and I can easily include them in my regression. That'll work just fine, and here are the results. But you may find this somewhat inelegant. I suppose it's a matter of taste. I find it a bit inelegant to create columns that I don't need except to run a regression. It seems like I'm sort of wasting information somehow, or rather wasting space when there's no new information. So an alternative, and one that I tend to prefer, although you may disagree, is rather than constructing new variables, I could just change the formula. So here's how I would do that. I would just have my lm command, and I would put log of kid score, tilde, mom age, plus, this is a bit weird, I of mom age squared, comma, kids. This gives exactly the same results as the previous slide, except the labels are a little bit different. Okay, so what is this I? Well, the key point here is that a caret, the thing that I use to create a power, raise something to the power 2 in this case, has a special meaning in our formulas. We haven't talked about it, but it's in my R formula cheat sheet. So in order to use that character to take on its original meaning of raising something to a power, we need to escape it by wrapping it in I. What I does is it says, hey, R, everything inside of these parentheses should be treated as is. Don't try to interpret it like it's a formula. Just try to interpret it like normal R math. We don't need to escape log because log is not a reserved word inside of formulas. It doesn't have a special separate meaning, but that would still work. So there would be no harm in wrapping the log inside of an I. It's just not necessary. We can also add interactions. So now I'm going to add an interaction between mom age and the mom's score. So to add an interaction x times y as a regressor, we use not x multiplied by y, not an asterisk, we use a colon, x colon w. So here I have mom age colon mom IQ. Alternatively, if you wanted to use a multiplication sign, you could use I to escape the multiplication sign. The reason you have to do this is because that asterisk has a special meaning inside of our formulas. Now, one thing I should caution you about is the regression I'm running here, which is a regression of kid score on the interaction mom age and mom IQ. That's a very silly regression to run because notice I haven't included mom age by itself and I haven't included mom IQ by itself. So this is basically a regression with an interaction but no main effects, which is kind of bizarre. If you don't know what I'm talking about, again, you may want to take a look at the document I linked earlier in the slides, very near to the beginning of the slideshow, where I go through the interpretation of all of these different regression models for the kid score example. And now it's time for you to try. I have a somewhat longer exercise for you to experiment with, and I will ask you to use ggplot at the end to make some more exciting plots than the ones we've seen so far.